All right, and so for calculus students of mine who are on track for either business field or any kind of social science or the health science major, then the whole Desmos green, the whole Desmos activity that I've been using so far, you are allowed to have a copy of this activity right here, so that you can have an interactive the little portable tool to calculate a lot of areas, and for the simplicity of your course, you are allowed to use this. So I have sent a copy of this to your main course learning website, so you can find out contact with me in particularly individually to find out where I put this file, because I teach at different places. But in the end, the reason I want you to have a copy of this, because in the next activity, I want you to be able to follow along and have some fun with doing these approximation of the areas problem right here, and as well as the Riemann sum problem. Okay, and so once you have had and it's simply just a link that you will be either forwarded to you through the school email, or as I said, I have uploaded on your the main course website, and it's simply just a link. And so once you open the link, then you have the exact thing that you are seeing on my screen right now, so that in the next activity, so I highly recommend that before I head out to the next activity, you can go ahead and contact me to obtain that. So pause the video right now, contact me to obtain the link here, and then once you've had the link, you don't even need to log in or anything like that. Once you have the link, you can just simply copy and paste the link right into a web browser, and it will open the exact activity as you see here, and then we will have something to work together. Okay, but so now I want to use this activity for the following work right here. So let me get back on that example 1 that we have seen previously with Riemann sums and discussions. And so we're close, we're close to getting to a solid understanding of what a formal definition of what a Riemann sum is, the left endpoint, the right endpoint, and all that. But so now let's stay with the exact same example, and I want to have an extra activity for my calculus students who are on track for business field or any kind of social and health sciences major. All right, so the same problem here, but now, as you can see that throughout our discussion earlier, the more sub-intervals we have, the better it will be. Okay, and so now I still stay in this example, but I'm going to produce, how about part C right here for that example. So let me move over to the other board. But the idea now is that, and this is why I mentioned earlier that I allow you to use the exact Desmos the activity, the exact Desmos tool that I've been using. I prepared that myself so that you can have the interactive calculator to go and do the work along with me. So let's do the approximation, but how about using L8 and then how about L16? Okay, L8 and then L16. So if this class here is the class for the calculus students who are on track to an engineering major or math major formally, or a physics major, then they will have to learn the kind of technique to do this without the calculator. So the students there don't get to use the Desmos thing that I'll share with them. But for students in business major, on track for business major or health and social sciences major, then you are allowed to do this. And so my approach here in this part of the video is particularly to aim at viewers and audiences who are on track to business field or in a course that's simpler than the formal calculus course. Okay, even though they're all calculus. So L8, yes. Tentatively, the idea now is that the whole interval from -1 to 2 right here, we're going to break that down into 8 subintervals. So that's what we're heading out for right now. So each of these, I'm going to cut that in half. Okay, and that's the reason why I'm saying, I don't want to spend my time and wasting your time of chopping down these values anymore. Let's have Desmos show you the picture. Okay, so on Desmos right here, and this time I show you the full screen, which is exactly what you will see once you have obtained the exact same copy of this program I'm using here, this interactive tool that I have developed here for my students. And so these are all the control right here, and the functions we are using here is still the x squared function, and that's being shown right here, and this is what you will see. And then the starting point of your interval is at -1, and then the ending point of your total interval is at 2, just like how it was here in the activity, and we want to find the area. So the graph I draw as a hand sketch here still looks just like that you've seen with you will be seeing with your Desmos right here, and right now you are seeing on my computer screen. Okay, and so now here's what I'll be doing. So we are doing L8 for now. That means we need 8 subintervals. So this line right here, when you have had a copy of my Desmos activity here, then you can switch this, or you can just slide the slider. Okay, you can just slide the slider here to 8. Okay, and if sliding is a little too challenging, you can just manually type it in, use your mouse and click on that, and then highlight it. Okay, and type in the number 8. Okay, and then simply click outside of that. Okay, so now if you notice on the interval here, the partition has been broken down into 8 subintervals. Okay, so you have 8 subintervals. -1 is here, 2 is here, and these are all the 8 subintervals. So Desmos has taken care of all of that for you, and you don't even need to calculate all of this. I want you to quickly explore and have fun. And so I also have prepared the value. So this is what happened. If we are doing 8 subintervals, so this Ln right here is now, of course, L8. And so I have already programmed Desmos to calculate the answer here. Okay, so that answer now is going to be 2.507. And so if you already had a copy, you can go ahead and do along with me. See, go to this line, change that to 8. The picture will immediately show the partition of all the subintervals here. And if you want to see the picture, see, click on this little empty circle right here. Click on that, and whatever I programmed there, it will show the picture of the 8 sub-rectangles being displayed here. Okay, and so I hope you will have a little bit of fun time exploring. So now if we increase the same exact area that we are trying to approximate with 8 subintervals, and we got 2.5078125 right here. Okay. And so I'm going to now quickly switch back over to my writing board there, and I'm going to just simply write it down. So I don't even need to nail down all of these partition points anymore. But so here I have to admit quickly as a discussion here, well, I'm just going to make a note and to give credit for Desmos. Thanks to the engineers who came up with this website right there. But L8 now came out to be, okay, and in what Desmos gave me, 2.5078125. All right, and so the area now as conclusion. So we're experimenting that the area that we're looking for is can be approximated by L8. Okay, and so now instantly the same question here. See, that's why now having Desmos and things go a lot faster. We don't have to do the manual calculation. We already left it all for Desmos.com. Okay, so now I'm going to immediately switch over to L16 right here, and let's find out. So I'm going to switch back to the computer screen. And so now on my computer screen, which is still currently with 8 subintervals. And now I'm going to quickly switch that. So you can either use a slider, but for me with my mouse here, slider, it doesn't work too well right here. So it's not precise enough. So I'm going to quickly click on that value and highlight, and then I'm going to type in 16. All right, and then I'm going to click into the graphing area outside of these controls so that it will clear out of that entering mode. And so now you can spend some time counting, but Desmos really does a good job in terms of breaking it down into the subintervals for me right here. Well, it did take me a little bit of time working around to create this activity, to program this work right here. So that's the picture. Okay, and if you don't want a picture anymore, you can just hide away, and that's only it will only leave behind all of these partition points. And we don't. If you want to, you can click on the partition points. Click on that. It shows you where each one of those x values. See, these are all the x values of the partition points. Okay, and now, so this is now n is currently 16, indicating we're looking at working with 16 subintervals. So of course this L here is L16, and that's the value. Okay, and we got a higher value here. All right, and so now I'm gonna quickly get back to my board here, and this time with Desmos.com I found out that L16 here was quickly calculated, or conveniently calculated for us, by Desmos being 2.736328, and a lot longer. Maybe I still have enough board space to write the rest, so 28125 right here, and that's all right. And so now we can say that the area can be approximate even better with L16. Okay, with L16. All right, and so in that same way, see, and how quickly we already have taken care of two little different questions in one question of part C. So what about using Desmos again? I'm now going to call that question D, the same example. Okay, same example, but let's look at or 8 or 16, or 8 and or 16. How's that? Because what's the point of having Desmos.com being so powerful? Okay, at least it's powerful enough for the kind of work we're doing here. All right, so now with Desmos already on screen right here, and I don't have any of the picture yet, but see, so now let me switch back to 8 right here. All right, and click outside of the area. The picture of the Riemann sum, right hand side, I call that I named that Right Riemann. Okay, and then for the left rectangle, I call that Left Riemann. But I click on that to show the picture. So that's the picture of right there is 8 subintervals. Right now we get back to 8 subinterval. N equals 8 right here. So Rn or R8 right now is specifically this right down here. Okay, so the value here reached 3.6328125. Okay, and so that's what it is. And we can quickly put that on the board. So now with Desmos.com, life went a lot easier for us here. So R8 right here, okay, is going to be just simply 3.63 28125. It's not the exact area that we're looking for yet, but once again, the area we're trying to achieve can be approximated by this R8 value, by R8. Okay, so that's what we can do. And so I'm still going to leave this here. Let's look at how about R16. So now on my calculator screen over here on my Desmos.com, okay, I'm going to change this to 16 subintervals. Okay, 16 subintervals. And so now clicking outside of that. So now if you notice at the bottom right here, the number has switched, Rn now has switched to 3.29. So it's a little bit down because you can see that the amount of overflow, the amount of overestimate has been shrunken down right there, has shrunk down. Okay, so in that way, okay, now we can have an answer to write that on my board right there. And see, we did not have to do any manual calculation any longer. So now R16 right here will be now 3.2988282125. A lot lengthier, but that's the value right here, and it does seem to get a little bit less than R8 right there. But and then tentatively, this is the kind of answer that that gets closer to the actual answer of the area we're trying to achieve. So that area now can be even better approximated by R16 right here. Okay, and this is even the better version of that. I have to say that. Okay, so I hope you have some good fun with Desmos activity that I have shared with you. Okay, but that is now how we're done with example 1 right there, where we start out doing part A and B with the manual calculation where I show the step. And of course, if any one of you is patient enough, did all of the activities we've done with Desmos, you can also repeat all that if you have time to invest into that. And the more you spend time into these kind of problems, no matter how many rectangles you want to break it down, but the more you put your time into it, the better you will get at this kind of skill right there. Okay, so that's everything about example 1. And so now we're at that point here to understand a little more clearly now. And we're ready to make our way into formally defining what it means by being a Riemann sum right here. All right, so I need to have you look back at the video, so maybe rewind the video possibly to look back at the activities I was doing with the x square function from between 0 and 1, and then from any of the example we have done just now. Okay, but mainly the idea now, and I still have that on my calculator screen here as well. So let me give it a little bit of time to prepare all this. Okay. All right, so back on our computer screen here. So we only need to say with the 4 subintervals, and then we will get a lot of good ideas out of that already. All right, so this is what we did. The whole idea now is that one interval that we're doing, and even let me roll back to the beginning problem that I promoted, that's where we start from 0 to 1 here. Okay, so from 0 to 1, the total interval here, okay, we broke that down into 4 subintervals. That's the first activity that we did right there in the. All right, so now the general idea now is that you have a function. And this is, now I'm having my final opportunity to continue with that generality I brought up earlier. That, so we have a function. Our first activity was the x squared function, but the idea now is that it's some function being continuous function. And of course defined in the certain interval that we are working with. So the interval here is from A to B. And so now inside of that interval, we're looking at the promoting problem. Now I have to be clear, the promoting problem here is that we want to estimate, we want to find the area inside of that part, trapped between the curve of the function and the x-axis, and between from A to B, our starting point of the interval to the end of the interval. Okay, and so this is what we did right here. We broke that down into subintervals, and that's what we did. So I even did this earlier. I call this interval number 1, interval number 2, interval number 3, number 4, and if I even broke it down into more intervals, and 1, 2, 3, 4, 5. But no matter how many intervals I want to break it down, but it's all being limited in this overall interval from A to B right there. And so that's why you have seen earlier, and I trigger your thinking a little bit earlier, that the more subintervals we're attempting, then think about how it changed our intervals here. Each of the subintervals width right there. Okay, but so now the idea of instead finding the exact area, that's the work right there. We couldn't do that yet because we didn't have any definite formula. So we did that by So for now, we are already through with that step. We're breaking down into subintervals in equal widths. Okay, so the width here is always b minus a over n. That's something else I also need to remind anyone again. So each of the width here is b minus a, the total length divided by the number of subintervals we're working with. So for now, just think about 4 of them. Okay, and then from that point right here, see, if we pick any interval, let's say pick interval 2 right here, then between the interval, then we have our choice to pick. We have our choice to pick a point either the left or on the right hand side. Okay, and so generally speaking, at this point, allow me to introduce this. The left endpoint in any interval. So any of the interval here, let's say at this particular interval, I'm going to call that the interval 2. So the left endpoint for interval 2, I call it x2, but with a superscript L right here. So on interval 2, that's the left endpoint that we chose. Okay, and so generally the idea is this: we picked the left endpoint, okay, in that interval 2, and then we plug that into the function, substitute that into the function. That's to get height of the rectangle, because eventually we're going to draw the rectangle. So see, if we're doing that, then it's going to give us the height is determined by this. And so from that, we're going to draw over and get our rectangle. All right. And so in that way, that's the height for rectangle 2. And then we multiply with the delta x, the width. So that's for one rectangle, and specifically rectangle number 2 right now. So that generality there was for all other subintervals. So at any I subinterval. So so now that was specifically at second rectangle number 2. So now I'm going to talk at I'm talking about generally at ith subinterval. And specifically, let's look at the left endpoint for now. Then this is what we did. We picked the left endpoint. So at the ith interval, it's x sub I. That's what I'm doing. And then the left endpoint right there. And then substitute that into the function and multiply that with the width that was previously calculated. That gives me the area of that gives me the area of the ith rectangle. Okay, so rectangle 2, that's x2 on the left. Okay, and substitute into the function and multiply with the dx. Okay, and so, but then that's not all of the work we did. This is only for one rectangle. This is, see, that's why I'm saying at some ith subinterval, right? We created the rectangle with the area being done as indicated here. And so the generality that in the end, the work that we did there, and now I have to really explain right here. So we have to start out all the way from first. This is now number 1, first rectangle, but picked left endpoint, substituted that into the function to find the height, and then multiply with delta x. That was area for the first rectangle. Then we accumulated that. That's why I'm having an adding. So we accumulated that with the height for a second, or for a rectangle number 2. That's why x2 right here, but on the left endpoint. Okay. So the height here, see, rectangle number 2. Left endpoint being substituted into the value, into the function to find the height, and multiply again with the width. This is area for rectangle 2. This is area for rectangle 1, and then so on and so on. And so the function at x3, this is the value in the third interval on the left endpoint. Okay, that's what the superscript L is for. So this is the height of the third rectangle multiplied with the width again. And see, in a general setting like this, we can go to as many n as we want. That's why I'm leaving dots right there. Okay, but we're doing all the way to the last one. So if we have n subinterval, we go x sub n. left endpoint on the n interval. That's what this x sub n superscript L is for. Okay, and times delta x. So this is a general setup. But see, this right here is what we now formally refer to that as the Riemann sum L sub n. Okay, or so a little more formally, you are welcome to use this long version, or there's a more condensed version, which is because it's a sum. It's a sum. So usually when you arrive at a calculus class, then your mathematical majority is higher now. It's higher. So you are ready to accept. To take the symbol. It's a summation. We sum all of the. You see, generally at any of these area right here, the formulation is that it's the left endpoint at any ith interval, generally at any ith interval, substituted into the function. That's what the f at x sub I to L right there, superscript L, multiply with the delta x. Okay, and then we're summing all of those little areas. In areas, I keep using the term area just to have you have that envision, that visualization about every single thing we do in here it came from that original promotion right there. But that is formally now we define that. Okay, so now as a definition, now as a formal definition, this setup right here, or in this setup right here, is now called and it's just a generality we drew out from throughout doing our activity, and so it's now called the left Riemann sum. All right, it's called the left Riemann sum, and I will come back and point out more details about this. But right now, as the way how it looks, it's just simply starting with the interval. It's all about we start with an interval. Okay, and you don't even have to think of that as area. We will get to that and even clear with that idea with just simply you got a function and then and a given interval. And so at least in that given interval, now we define the operation, the kind of work we define, the kind of work that we break the interval into equal with subintervals. Okay, and there could be just 4 here, or there could be a lot more. Okay, but then each of the width now is the delta x. We can calculate that value by b minus a over n. Okay, and then so on each particular ith subinterval, we formulate the following. We formulate the idea now is that, so if you don't, I start recommending to think of this as just simply the function value at the left endpoint on any general ith interval right here, any general ith interval, instead of seeing that permanently as an area. I don't want anyone to get your mind completely stuck with the idea of area. Okay, because at some point later on, Riemann sum and areas will at some point depart from each other. Okay, but so for now, all I want you to understand is we define the work, we define that operation by, hey, at any general interval, we pick the left endpoint, substitute that left endpoint into the function, and so we get a value, and that's why as a picture the value is the height of the graph at that left endpoint. Okay, but then having the height right there, I call it the height because I want you to associate with the picture, but it's just simply the function output at the left endpoint on the given ith interval, and then we multiply with the delta x. And then we're not doing only for one interval, we're doing for all intervals, for all subintervals we've had. And so in that way, and then once we've had all of those products right there, from all of those products, nail down, we're going to sum up all of those products. That's what the Riemann sum is. Okay, and then in specifically each of the products here, that function output here came out from the left endpoint on your particular subinterval there. So that's why we call this, it's the left Riemann sum. Okay, so in that way, same way, I'm going to roll back to my board. And now, instead of doing, we also did this back in our earlier activity, back on the x squared function. The same way that we already have broken down our interval into subintervals, equal widths, of course. Okay, and so now this is what I'm doing. Say, for example, third interval, or we can still stay with second interval, but for third interval, instead of using left endpoint, I'm going to use a right endpoint. So I call that a little different symbol over here. So on the third interval, I pick the left endpoint. That's why it's the x value on the right endpoint of the interval number 3. Okay, substitute that right endpoint into the functions, and so we get something like this. We get something like this, interval number 3, but use the right endpoint. I'll get something like this. Okay, that gives me the height, and then from there, I'm going to create my rectangle as that. All right, so that's the rectangle. So on rectangle number 3 right here, I pick the right endpoint, substitute that into the function to get an output, and that output there is multiplied with, or being taken as a product with delta x, calculated previously here. Okay, and then we're going to do the same for the other rectangle. So say back to number 2, now instead of picking the left endpoint, I'm picking the right endpoint, so right endpoint goes as high as right here, and drawing over, that's my other rectangle. Okay, and so that means generality, as a generality here, then at any ith subinterval, then we're going to, instead of picking the left endpoint, we pick the right endpoint. Okay, we pick the right endpoint on that. And so at the ith interval, or on the ith interval, we pick the right endpoint, okay, and substitute that into our function to get an output. And that output, we usually envision that or visualize that as the function's height at that point x sub I on the right endpoint. But then we multiply that output with the width dx right there. And so now moving over to my other board, we're not only doing that for one particular interval, but we're doing that for all of them. So now allow me again to come up with that general formulation here. I first tried to retain some of the stuff we've had, but I decided to erase everything. So here, think about specifically at interval number 1. Then the right endpoint now is going to be notated as x sub 1 for interval 1, but right endpoint on first interval. Substitute that into the function to get some kind of output, to get an output value, and multiply that with delta x. That's what we did. Just the work we did here, but for first interval. And then, as I said earlier, we're not only doing that for one interval, but we're doing that for all intervals. If we break it down into like 100 intervals, we have to do from x1 all the way to x100. And so f of x2, that's for interval number 2, as the right endpoint on interval number 2. That's x value specifically gets substituted into the function and multiplied with the difference dx, delta x right there. And we're going to start accumulating those. And again, I'm going to repeat that for the third interval. Okay, so x3 superscript or multiply with delta x. And I'm going to keep adding more until I reach the last one, the nth interval of mine. When I reach the nth interval, then it's going to be f of x sub n to the r. So the n here is a little bit different with the I. I should have also mentioned that when we were doing the ln earlier. But it just means this is really our last one on the list. If we break it down into n subintervals, then x sub n here, or x sub n or is the last right endpoint on our last interval. Okay, and then we multiply that with delta x. So the n here is different with the I. The I here was just to indicate that when we're at any interval before the end, or it could also be any interval from the beginning to the end. That's what the I is. But now this x of n here is just for the last one. So that sum right there, we define that to be Rn. That's what it is. Okay. And so now, alternatively, we have the summation notation. This Rn is defined as the... So basically, I want my viewers, my students to start seeing this simply as an operation, a work that we define. Start departing away from areas. Any of this is just an output at the right endpoint of the function in that interval 1. Multiply with delta x, already previously calculated. Then this is function output at the right endpoint on interval 2. Multiply with the delta x, and so on and so on, and we sum it up from the beginning to the end. And now, that's why in that way I have a summation notation. So if we're summing all the I from 1 to n right here. Each of the index right here, we're looking at taking the right endpoint on any of the current ones, okay, substituting that into the function and multiply that with the delta x. Okay, and so summing it all up, it's just what that sum is, but instead of the lengthy descriptions, we're going to write in the shorter descriptions. I recommend that know both of these, be flexible with any of these. Okay, and so this is now called so that sum, like the sum defined like that, is called the Right Riemann Sum. All right, the sum like that is called the Right Riemann Sum, like that. And so now, I even have to push your thinking, because Rn, Ln is just one of the two cases, one of the two specific cases of the more general version of the Riemann sum. We haven't reached to the main general understanding of the Riemann sum yet. So what exactly is the Riemann sum? So now, allow me to erase this. Okay. So now let me just completely speak on behalf of any general ith subinterval. So at any general I subinterval, then we can have the following. So in any I subinterval, we can either have, and as I already mentioned, it's just a choice right there. On the ith interval, we can look at the left endpoint, okay, or the right endpoint, because these are both two different components of your ith interval. Any interval has to have a left endpoint and a right endpoint, so any one of these belong to your ith subinterval, or it's an interval, it's a point of that interval, a point of that interval. Okay, either the left endpoint or the right endpoint. It's a point of that interval. And so now I'm going to generally define the following. I'm going to how about call that just a C point. Okay, so it leads me, so knowing that, either being a left endpoint or a right endpoint, just simply a point, just a point of that interval. And so it leads me to this following understanding. I'm going to call that it's a C point. C sub I point. That means it's just simply be a point. It can either be the left endpoint, or the C sub I can also be the right endpoint. Okay. It's only a choice between these. That's why I'm saying, we choose that, and maybe that's the reason why I call it C. It's a choice, but that choice can be the left endpoint or the right endpoint. But when we stick with one, we stay with the rest. Okay, once we stick with one, and when the rest of all the other intervals, you have to stick with that same point right there. Okay, so here's the actual general Riemann sum right here. So the whole idea of the Riemann sum is that instead of focusing specifically on left endpoint or right endpoint, now I can just say on each interval, I can just pick a point of that, a point I, a CI point. I'm a little bit ahead of myself. This is C1. It could be left, it could be right here. Okay, but once it's left, it's left for the rest of it. Once it's the right endpoint, it's the right endpoint for the rest of all these guys right here. but it's a point of the first interval. It's a point of the first interval, 1. And so in that way, this x2 or here, that's a little too specific. Generally, we can regard to this as a point C2. Left endpoint or right endpoint is just a chosen point, okay, of subinterval 2, okay. But like I said, if we already decided to stay with left endpoint and all of these guys are all left endpoints, if we chose a right endpoint and all of these guys are right endpoints, okay. And so now I can modify this version, okay, as a C3, okay. And so same way here, I can modify this final one, this last one for our last interval as a C, and they're all lowercase. That's what I meant to write with that. And so this right here is a sum. It's a sum. And so, but I can't call it L because L is more specific as using the left endpoint. I can't call that R because it's a little bit too specific as it's already specifically used as the right endpoint. So here I'm just going to call it, it's just some kind of sum, okay, by summing up n terms. Okay, it's a sum by summing up n terms. Each term here is done by picking a point of the interval either on the left or on the right. Substitute that into the function and multiply with the delta x. Same thing here for second interval. Pick a point, and now whatever you chose here, we chose the same one there. Okay, but it's the same agreement with that. But pick that point, substitute into the function, and evaluate and get some output. And so we're summing up all of these terms from beginning to the end. We have this is now, or in summation notation. In summation notation, it's a summation f ci multiply with delta x. Okay, and summing all from the first term to the nth term right there. Yes, that's, we call it s of n. And I have to admit at this point, this s of n right here is actually just my own term. Believe me, I've taught calculus for years, and I've seen many different textbooks using different the symbols here. So some textbook might agree with my symbol, some textbooks use other symbols right here, but in the end it's just a sum. Okay, and we created the sum this way. Now the L sub n symbol, the R sub n symbol, I agree with many other textbook authors because that's probably the best way. But when it comes to the general version that I'm introducing here, some other textbook use the symbols here. So that's the part where, be flexible with me on this. So I'm using S of n textbooks. We'll talk about this kind of work as well, but may use different symbols here. That's what I'm trying to point out right there. And so now this definition, this sum right here is called, okay, it's just a definition of the kind of work we're doing here. And when we do that kind of work, we call that, we're taking the Riemann sum. Okay, so this is called the general Riemann sum. Okay, and just the Riemann sum. Forget about the word general. I write it here, but I'll put it in parentheses. Okay, the main term here, because you can skip the word general. This is just called the Riemann sum. All right, so that's formally what the Riemann sum is. Okay. All right, so now after having a careful discussion and explanation of the formal definition of what it means by a specific left Riemann sum or a specifically right Riemann sum, and then we led our way into a general definition of a Riemann sum in general, then we are ready for doing an example over here. So let me clear out my board. So now keep in mind that at this point I start wanting my viewers, my students who study this video lesson with me to start seeing the Riemann sum as just simply a sum that we define. So once we see that instruction, we work that way through the problem. And you will understand what I mean by as we get into this example here. So now I'm going to call it example 2. All right, so on example 2 right here, we are given a function being a continuous function. How about x cubed? Okay, and this function, and that's all we are having for a function like this, and I want to, let's evaluate. So this time, instead of saying approximate, we actually evaluate, okay, part A, or 4. Let's evaluate or 4 on this interval from 0 to 1. Notice in my instruction of the example here, I did not use any word area at all. I did not get to that point of completely making you depart from, making my viewers, my students to depart from areas and Riemann sum yet. But it will come after we finish with this problem. So the point of this example here is that I want you to simply take the problem here solely or entirely as a problem where we're summing up. That's all. We're just summing up. Forget about areas. Forget about areas. So we have an interval from 0 to 1. Our function this time, at this point I'm seriously getting tired of my x squared function. So let's switch over to x cubed. Okay? And then when you are more mature in math, and you can do the same work here on other functions as well. The interval is from 0 to 1. I want to find our, so let's learn to speak it out a little bit, okay? This is, we want to find the Riemann sum, the right Riemann sum, using 4 sub-rectangles, using 4 sub-intervals to be precise, on that interval specifically given here. And as it said here, it's a right Riemann sum. That means on each of the sub-intervals here, I'm going to pick the right endpoint to get my function evaluation. Okay, so here we go. So let's look at a couple prepping steps right here. Delta x equals, see, and at this point we're so clear that it's completely legal that we're using equal widths. So 1 is the final point, minus 0 is the beginning point of our total interval, divided by 4. We want 4 subintervals, so this is 1/4. Or in decimals, if in case anyone is more familiar with decimal, 0.25. Okay, and so now I'm going to use my next board. And let me spend some time erasing it. And now again, for this particular example, if you are working along the way with me, I highly recommend, it's entirely a math problem, but we're not worrying about the area picture or anything like that, okay? So again, it's a good habit that we're doing this. The interval from 0 to 1 on the line of numbers. Okay, so on the line of numbers, there's our interval from 0 to 1. I'm going to break it down to 4 subintervals as instructed. As instructed. Okay, and so now in that way, this is 1/4 because, or 0.25. This is 1/2 or 0.5. This is 3/4 or 0.75. Okay, so in that way, this is how we're doing the OR4 here. OR4 will be done by, it's a sum, but for the first term of the sum, here's what we're doing. It says OR, that means now look right, the first sum, the first term of the sum comes out from the first interval. Interval 1 is here. Okay, and see, I don't even need to worry about what graph is the x cubed function. Interval 1, interval 2, interval 3, and interval 4 right there. Okay, so the first, so on the first interval, the instruction of the problem says I want the right endpoint. So on the first interval here, first interval, the right endpoint is this guy, 1/4. So now I'm going to have to take the right endpoint, substitute that into the function. And then I'm going to multiply with the delta x that we have calculated previously, 1/4. Okay, let me quickly swing back to the other board to convince you. This is our delta x value. Okay, and so, and now, see, that's the setup, the general setup for how we're doing that. Okay, and I completely ignore, I don't even want to mention about the graph of the x cubed function or whatever. If you know it, it's good for you. It's not needed for our problem here. Okay, next term. So now we're done. And don't even think about areas of rectangle or anything like that. That's not what we need. Now we're moving on to the second subinterval. The second subinterval here is okay, right endpoint again. So right endpoint on the second subinterval is 1/2. So f at 1/2. See, I take the right endpoint. The rule for all the terms here is that at each term I'm going to take the right endpoint on the interval correspondingly. Right endpoint, substitute that into the function, get some kind of output eventually, and multiply that with the delta x that we have calculated previously. That's what we're doing. Okay, and now I'm going to add that to the next one. Okay, so on the third interval, because we're done with second term, on the third term, that means we're at the third interval. So 1, 2, 3, right endpoint is here. So f at 3/4. I'm going to 3/4 there. I'm going to multiply with 1/4 being our delta x. Okay, and I'm going to add with my last term. My last term comes out from the fourth interval. So right endpoint of the fourth interval is 1. So now f of 1 times 1/4. Okay, see how easy we can follow that setup right there. And of course, if you are a little more experienced with running the summation symbol, I'm not against at all that you are using that, but in the end, when we really are adding it, it's all going to be like this. So from 1 to 4, okay, all of the f of some c sub I right here, right, and multiply with 1/4. And then in the end, we're still going to have to spend some time breaking down the c sub I right here. Okay, all right. And so I'm not going to specifically going in that route, so I'm going to stick with this long sum right here. But you see the general idea. So now, throughout all 4 terms here, we're not doing an area problem. Keep that in mind. Okay, they're all having common factor here. We have our legitimate rights. Pull that out in front. Now in parentheses here or in brackets here, see, function output for 1/4 is going to be 1/4 cubed this time, because the function given here is a cubic x cubed function. That's why I'm doing that. Now plus f at 1/2 will be 1/2 cube. Should have done that. F of 3/4 is going to be 3/4 cube. Okay, and f at the last one here in our work is going to be 1 cube, and then we put that in brackets. Okay, and so that's how we're coming closer and keep getting closer to getting our final answer of R4. And I'm talking about R4. I'm not saying anything at all about area. All right, so my final calculation show R4 equals 0.390625. That is our answer for this particular problem. Calculating, evaluate the actual value of R4 right there. All right, and so now we are ready to make our way out to part B of the example. So it's just another question right here. We're still staying with the same function f of x given here to be x cubed, and we want to evaluate. But here in this case, I'm going to change to a different question. All right, so how about for part B here, let's look at we want to evaluate L4. So learn to speak the name of these symbols now. So L4, the capital L4 means it's the left Riemann sum using 4 subintervals. And so we already clearly defined a Riemann sum at this point is not only an area. I mean, the area is the best place where we apply the Riemann sum idea, but the Riemann sum on its own is just simply an operation. We define the operation that, hey, we break it down, we break our interval down, so here's the interval. We want to find L4 on the interval from 0 to 1 again. And so back to what I was in the middle of saying, we want to break this interval into 4 subintervals, and then from there on each one of the interval, on each subintervals, we're going to pick the left endpoint, and then we're going to produce a sum. We're going to produce the sums, etc., etc. And so I'm going to start making my way out to the other board so that we can get started on that. All right, so since we're looking at the exact same interval and with the exact same number of partition points, the exact same number of subintervals being required here in the problem, and so it's good that I can still retain this exact chart here. So there's our interval from 0 to 1. I broke that down according to part A of the example we were now doing. Then we broke that down into 4 subintervals, and I had the red numerical labels here in red ink over here. And so each of the space here, maybe I should always get anyone into a good routine in case the problem here was the only one problem and as an independent problem itself. So delta x is always the final point of our interval given minus the beginning point or the initial point divided by the number of subintervals we want. And so our delta x for this problem here, finding L4, is going to be 1/4 or a 0.25. And that is the reason why now I can legally use the chart here that I have made for part A of the example. So that's exact same chart here. I broke my interval down into 4 subintervals, so consequently each of my delta x here has to be a 0.25 or a 1/4 in space. And so now in that way, consequently it's easy now enough to see how these partition points are being calculated here. So 0, and the first one here is a 1/4. The next one is has to be a 1/2. So and values go increasingly up to 1. All right. So for now, for the L4 that we're specifically looking for, the left Riemann sum with 4 subintervals. So now in the first interval, so just like that, the Riemann sum now just tells us that, hey, in each interval, for now, as for the first interval, I'm going to pick the point as designated here be the left. So I'm going to pick 0, the left endpoint, and substitute that into the function. And that's an operation. It's a work that we do, not necessarily to find area. And I will get back and emphasize this with a better example later on. But now, once we've had that output, we will multiply with our dx here, in this case being a 1/4. Okay, that's how much that space here in each of these subintervals. And now I'm gonna, so that takes care of the work that I did on my first interval. Then the second interval, now once again for the second interval, left endpoint is at 1/4. So I'm gonna substitute 1/4, the left endpoint of our second interval, into the function. And I'm gonna multiply with the width again. The width of the interval is 1/4. Okay, and then for the third interval, interval number 3 now, left endpoint is 1/2. And so now 1/2 is substituted into the function. And then same way with how we define a Riemann sum here, I'm going to multiply that with the delta x quantity, which is permanently a 1/4. And then we're going to add that to for the last interval, left endpoint is a 3/4. And I'm going to, again, substitute this value, this left endpoint, into the function. And then multiply that function's output with the interval with delta x equals 1/4. And so now we already, and see, when we were looking at this problem here, I moved on, I went over these problems. I was going over these problems completely without the graph, without switching back and forth from the graph and showing the graph, because I want my students to learn this problem in this current example entirely as an evaluation problem that we just carry through the process, the operation here, and we got an answer. And it's not necessarily an area problem, okay? And so now as a further step right here. F at 0, our function was an x cubed. So with our function being an x cubed right here, then so now I can get back to my function. So x cubed here is going to give me 0 cubed times a 1/4. And I should also continue the same practice I've been doing. I recognized a common factor of 1/4 in each of our terms here. So why don't we factor it out? So maybe I'm going to write it down in a little bit in the lower line right here. So 1/4 is being written as a common factor. And then first term in my parentheses, instead of writing f of 0, I no longer need to do that. Now we can just go straight forward into 0 cubed as the value being substituted into our x cubed function. Then I'm going to add to the next term. The next term now, after pulling out the common factor 1/4, now we're looking at 1/4 cubed. Then the third term is going to be 1/2 cubed. And the last term is now going to be a 3/4 cube. All right. So that's the setup that's ready for getting the final answer. So I'm now again going to quickly step back to my computer to get some calculated results here. All right. So my final answer now shows left Riemann sum with 4 subintervals is finally calculated as 0.140625. Okay, and one more time, let me double check to see whether I've had the correct answer written down. And yes, that was the value. Okay, and nowhere throughout this problem and the earlier problem in part A that I mentioned about an area, the answer here is good that we use that to approximate an area, but it's not necessarily always an area. It doesn't always mean an area. Okay, and so now I'm going to clear out my board again. And same problem, same function. I want to evaluate in part C here of our example. How about we're going to evaluate R4 again. Okay, so we're back to doing R4. So we're going to be doing similar work with what we've done in part A. But this is now, I'm going to switch to a different interval. How about -1 to 0? Okay, and the process some of the process will be similar to what we've done in part A because it's R4. And again, what is this? Right Riemann sum. It's a Riemann sum that we want to particularly pick the right endpoint on each of the interval, on each of the subintervals throughout this total interval here. And we're using 4 subintervals in this particular given total interval. Okay, and so again, first step as a common habit and a good common practice for anyone into doing any of these Riemann sum problems, we're going to nail down the delta x value. So delta x in our case here, final value of our total interval is going to be 0. So 0 minus -1. That's the beginning point of our interval. Now I'm dividing that by 4. So that gives me a total of 1/4 or a 0.25. Okay, and so now I'm going to advance to my other board, clear out the board, and then I am going to have to reconstruct this chart indicating all of the partition points because my beginning point is no longer 0. In this problem, my beginning point of the interval is at -1, and 0 is supposedly here at the end of the interval, of the total interval. All right. And so whatever can still be retained, I already had it up here without erasing it. And so now we can look at -1 being the beginning of our interval. And then 0 is here. So now with the amount of space being a 1/4 for each of these little sub-intervals here. And of course, forgive me again that I'm completely off scale. I'm a human being. There's no way I can compete with the machine in terms of precision. But so if we're having a -1 and we add with a 1/4 into that, then here we're looking at a -3/4. Okay, and a -3/4 is a negative 0.75. Okay, and then if we're adding another 1/4 space to the right hand side, we're looking at a negative 1/2, which is in decimal negative 0.5. Okay, and so you stay with whichever the convention that you're more comfortable with. You can either go with the decimals or fraction. And then with another 1/4 here, you're going to look at a negative 1/4. So if what I said meant was if we add another 1/4 space to that negative 1/2, we ended up with that partition point being a negative 1/4 or a negative 0.25. And here, if we're adding that final space being a 1/4 to this current negative 1/4, we're ending up with that final point of our interval being a 0. And so now, after getting that chart there with all the partition points being successfully nailed down and labeled, and I still have my sub-intervals labels here. So we're ready for R4. So R4 in this case is going to be, again, the setup comes out as following. For first interval, I'm going to pick the right endpoint and substitute that into the function. So that's the process. I want anyone following this example to see this problem as a process, and we just follow through the process. We get some kind of calculated value nailed down. So negative 3/4 is the right endpoint on the first interval. Okay, and so negative 3/4 substituted into the function, and I'm going to multiply with the delta x. And our delta x is 1/4 in this case. Okay, now I'm going to move on to second subinterval. Subinterval number 2. Right endpoint is a negative 1/2. That gets substituted into the function. The negative 1/2 is substituted into the function. And we're going to multiply that function outputs currently for second interval on the right endpoint. We are multiplying that with 1/4, the delta x again. Okay, and moving on to the third, now we move on to the third interval. Then right endpoint is negative 1/4. So negative 1/4 is substituted into the function. I'm going to multiply that with our delta x that we have found. And I still have a little bit space now. So right endpoint for my last interval, or interval number 4 now, is 0. So f of 0 times the delta x 1/4. And so I have to write that a little squeezy into the other board of mine right there. But that's now the complete setup for our R4 calculation. In this particular case where we shifted the interval to a different interval, negative 1 to 0. And I said shift, the reason here is that we still stay with the same function, the same x cubed function, but we changed to a different interval. Okay, and so let's continue further. And again, at this point, I can start speeding up the process now a little bit. 1/4 is a recognized common factor, so we can algebraically pull it out in front. Okay. And then now left behind in the total parentheses here, I'm going to look at function output for f at negative 3/4. And so it's a negative 3/4 in parentheses cubed plus, and now a negative 1/2 in parentheses cubed. That's what this is for. And our function, again, as a reminder, it's a cubic function. Plus, now the next one here is going to be a negative 1/4 cubed. And the last one here is a 0 cubed. All right, so that's the calculation setup. Before I tell the actual answer, I want any one of you who are viewing this video, go ahead and get your own answer. And I want you to have a moment to think about this answer before I write down the answer I have. And then we're going to talk about it all together. All right, so now I have an answer. The answer this time for R4 in this interval is going to be negative. And let me spell it out loud, or how about on my writing on the board here, I'm going to write the sign as in red ink. So how about negative, and the actual magnitude here is 0.140625 here. So the answer is a negative. Okay, the answer is a negative. But then at least this is the final answer to our problem. The final answer to our problem for this particular question, with our given function here being namely f of x equals x cubed. I was asked, or I was instructed in this question, to find the right Riemann sum using 4 subintervals on this particular given interval here. And so the work here consequently came out. The work consequently came out being negative and negative what 0.140625. Okay, and so now I have to say, as far as being able to perform a Riemann sum problem, anyone watching this video at this point, being through with me on 3 different problems here, I believe you are fluent. As far as getting the answer down, we're fluent. But now, before I completely close down this example, let me bring that down and emphasize what I have been saying in the last maybe the 10 or 20 minutes lately. See, I keep emphasizing lately that a Riemann sum is not necessarily an area. Okay, and so here, this is what it is. So area, I have to be clear, area is the best place where we can use a Riemann sum to apply and find an approximate for area. But the Riemann sum itself, so if we're now looking at the definition a little more closely, then the Riemann sum itself is not necessarily an area. Okay, so see, back to that the general definition of a Riemann sum, of a general Riemann sum that I mentioned earlier. So all we need is, on any interval, on any ith interval, we can either take a right endpoint or a left endpoint. So I came to that ultimate general version where I call it as a chosen point in any ith interval, and substitute that into our function. See, so everything I'm doing here is simply an operation. We chose, we picked a point specifically of that specific interval where we're at, and we substitute that chosen point into the function. Okay, so that's why it's an operation. And then after that, the operation goes further. We multiply that with the known, the found, the calculated dx, delta x. And then we're summing up all of these terms, because we're not only having one subintervals, we're having as many intervals as indicated here, as many subintervals as indicated in the problem. And so we're summing up all the way from the first rectangle, and that's what our I equals 1 to I equals n is for. So if we have n subintervals as requested, see, that's what the symbol S of n is for. We want to create a sum with n subintervals that came out from n subintervals. And so on each interval, this is what we do. This is what we're doing to each interval, and then we're summing all of these little calculations from the beginning to the end, from the first subintervals to the last subintervals, okay, to the end subintervals. So that's purely and entirely and only what it is for being a Riemann sum. And so now the reason I keep convincing anyone viewing this video to start departing away from the fact that a Riemann sum has to be an area, nope, it's not, because here's why. So now look back at the result in our example 2, part C right here. It's still here on the board. The answer was negative. The answer was negative, and I wrote that sign clearly in red ink right here. The answer was negative. So here's the reason. If we keep thinking, if we keep tying the Riemann sum to an area and only accept a Riemann sum as an area, then we will be stuck with the idea that area has to always be a positive value. We will be stuck with that permanently. But nope, in this case, since we purposely define this Riemann sum here generally only as an operation where we're summing up a function output, right endpoint or left endpoint as a choice, a function output at a chosen point on an interval, on a specific interval, then multiply with a delta x. So the function output itself could be a negative, okay? Because some function could be, who knows? Some function has a certain area or a certain zone that falls below the x-axis. So these function outputs here in this case, or actually the negative vertical lines right here, the negative, the vertical side that sink below the x-axis, okay? And so that's actually what happened in this particular part C of our current example right here, because these function outputs here, a lot of these were negative. See, when we tear it down to these calculations, that one was negative. That one was also another negative. Okay, and any one of you watching this video can always pause the video and verify my calculation. That should be a negative here. That cubic, another negative. So it makes things more negative. It makes things even more negative, and that one is a 0. Okay, and graphically speaking, let me switch over to the graph right here. Here's our famous f of x equals x cubed. Okay, and so the interval of interest, the interval that we're interested in is here, from -1 to 0. And so the two tick marks that just now being displayed here, these 2 points are to indicate we're looking at the interval from -1 to 0. And so in that interval, we are breaking it down to 4 subintervals. So now I'm going to put in the partition points right there. So we got 1, 2, 3, and 4 subintervals. And now with these subintervals, see, if we really have to visualize the picture here, then this is what the right Riemann sum looks like as a picture. There we go. So now all of the rectangles, yes, they're still rectangle, but now in the way how I'm seeing it, the rectangles sink, all of those rectangles sink below the x-axis. And so consequently, they result in, this is negative height, another negative height, another negative height, and this height here is a 0 height right here. Okay, and so summing up all of the negative heights. So area cannot be negative. That's why I want anyone, when you start learning formally about a Riemann sum that I'm writing on the board here, when we learn formally about a Riemann sum, then Riemann sum on its own is not necessarily an area, and so we don't have to permanently tie a Riemann sum to an area, because if we're only strictly thinking of a Riemann sum as an area, then all areas have to be positive. That's the way it is. We cannot have a negative area, okay, because it's an actual physical shape. So for something physical, we can't have a negative area. But now Riemann sum on its own simply is an operation. So operation can be negative, can be positive. And so in that way, among all of these the function outputs at our chosen point on each subinterval, some of these outputs could be negative. Okay, and so that's why in this case now, a Riemann sum in general doesn't necessarily have to be always positive and doesn't always represent an area. It's just on its own and on its truest meaning. It's just an operation that we define here. Okay, and so now that's the whole intention. So hopefully after my explanation here, you're really gonna have to depart away from taking the Riemann sum only as an area. Okay, the Riemann sum is the best tool for us to approximate and find area, but the Riemann sum on its own is not necessarily an area. Okay. All right. So now we're good with this example. And at the end of this example, that's where we have finished looking at all the details about the Riemann sum. And as a matter of fact, these are the details that are good enough for the practical understanding where the students who are on track for business majors or health and social sciences majors need right there. But if a student who are studying calculus with me, who are on track to an engineering related career or a mathematical related career or formally math major or even physics major, all of those students, you will have to learn even a lot more details where I must have to offer in all of those details in a different separate video lesson outside of this particular one.